Hi everyone, so here we are on chapter 5, and chapter 5 is on gases. So if you remember gases from first year chemistry, this is where we learned the equations P1V1 over T1 equals P2V2 over T2. Also, we learned the ideal gas law, which is PV equals nRT. So we are going to review those equations, but first we're going to be talking about pressure and the different pressure units and stuff. So here we go. Let's start here with pressure. So look at these units of pressure. 1 atmosphere equals 760 millimeters of mercury, 760 torr, and 101.3 kilopascals. Okay, so you should know all of these pressure units, and these are considered standard pressure units, okay, at sea level. The 14.7 psi right here, PSI stands for pounds per square inch. We don't really use that one. You're not going to see that one that much in AP Chemistry. Same for the 29.92. This is inches of mercury. You're not going to see that one too often either. So just make sure that you know these main ones right here. I'm trying to highlight these for you. Okay, so make sure you know those. All right. Now we need to go over some converting of pressure units. So this is review. We've done this before, and if you have all of these pressure values memorized, then doing the conversion is going to be very easy for you to do. Okay, so let's take a look at this sample problem here. The pressure exerted by a gas is measured to be 0.985 atmospheres. Convert this pressure to torr and to pascals. So remember, always start with the number that's given to you in the problem, all right, which is this number right here. So then start off with 0.985 atmospheres. Okay, so since we have atmospheres here, we want atmosphere on the bottom. So then we use the 1 atm on the bottom so that those units will cross out, and then double check and take a look what units it's asking for. The first one we're doing is torr, right? Converting it to torr. So we look at the value for torr, 760 torr. So that value will go on top. Equals. All right, so put this into your calculator and see what you get. All right, so then let's see if you did it correctly, and then I rounded my answer. I put 749 torr. Okay. Now what you want to do is now convert from atmospheres to kilopascals. Okay, so same idea. Start with the 0.9. I'm just going to put it up here. 85 atmospheres. This time we're going to kilopascals. Or it says pascals, but you can use the kilopascals. It's okay. It's just a form of the pascal. So then since we want our answer in pascals, I'm going to put the 101.3 kPa on top. K, I'm not writing K, PA. Doesn't want to write a K for me, but that's okay. All right, and then the 1 atm goes on the bottom. All right, so put that into your calculator. Notice the atmospheres will cross out, and then your answer will be in kilopascals. Okay, and then if you put that in your calculator correctly, you should get 99.8 kilopascals. Okay, you should always double check my math, all right, to make sure that it was done correctly. All right, now let's take a look at this other stuff here for Boyle's law and Charles' law, and Avogadro. So Avogadro's law is a new one for AP Chemistry. All right, some important things here. Don't forget when you use these gas law equations that the temperature has to be in Kelvin. Okay, that is so important for using these equations. The temperature has to be in Kelvin. These equations only work when the temperature is in Kelvin. All right, so then remember to go from Celsius to Kelvin, what do you have to do? Add 273. Okay, also in AP Chem, our STP values, you should be familiar with them. STP, once again, stands for standard temperature and pressure. So those are the standard temperature and pressure values that we use in AP Chemistry. Now, many times we use atmospheres. Well, in AP Chem we use atmospheres. Last year we used a lot of kilopascals, but usually in AP Chem we use atmospheres. So 1 atm and 273 Kelvin will be your STP values. So take a look at all of these other equations. You don't need to remember all of the names, Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law. You don't necessarily need to memorize all of the names, okay? You just need to understand the concepts, okay? The concepts. So this first one here, let's take a look at Boyle's law, all right? Boyle's law is a pressure and volume relationship, all right? A pressure and volume relationship. So in this case, the temperature is held constant. So let's think about what happens here, all right? Think of a container. So what if we, let me just go to a new page. So what if we start with a large container? So let me draw a picture of a large container so you can see it. So what if we have a large container? Okay, that is the volume. But now I'm going to make the container smaller. Okay, so what do you think is going to happen to the pressure when the volume goes down? So let's think about it. Look at the size of the container. You just made it much smaller. We had a large container. Now we have a small container. So now we're kind of squishing all of the particles. So what do you think that's going to do? So let's write this out. So the volume, I'm going to draw an arrow, went down, right? The volume went down. So that means the pressure, because you're squishing everything into a smaller space, the pressure is going to go up, okay? So what type of relationship is that when one goes down and one goes up? Do you remember? That is what we call an indirect relationship. You can call it indirect or inverse. It means the same thing. Okay, so that means when one goes up, the other one goes down. So let's look back at the help sheet again. So now let's take a look at the volume temperature relationship. So for the volume temperature relationship, I like to think of a hot air balloon. So I'm going to draw a picture on the next page. All right, so volume. The volume temperature one, think of a hot air balloon. Okay, so here's my picture, hot air balloon. Hot air balloon. Okay, there's a hot air balloon, right? Kind of. Let's say this is a little basket. There we go, that looks a little better. Okay, so here's my hot air balloon. Okay, so then let's say at first, the hot air balloon, here's the little basket, okay? So the hot air balloon is deflated and it's on the ground, right? So how do they get the volume of the balloon to inflate, to get larger? Well, let's think about it. What do they do in a hot air balloon to get that balloon portion kind of filled, the volume to expand? They add what? So they add, I'm going to draw another picture. They add fire, right? So here's fire. They add fire. So when they add the fire, then the volume gets larger, right? So let's write that out. So this is volume. So when the volume goes up, right, the temperature goes up. right? So think about what's happening to the particles when you heat up the particles, okay? So if you heat up the particles, more kinetic energy. Kinetic energy, once again, is the energy of motion. So the particles have more energy, therefore more collisions. Therefore, it's going to cause the volume to increase. Okay? Now, this is something that you probably experience in everyday life. If you ever have had balloons, and let's say you get these nice bouquet of birthday balloons, and then you go inside an air-conditioned room, you might have noticed that then sometimes they shrivel up and shrink, and that's because the temperature was, the air conditioning was turned on in the house or the room, therefore the particles were not colliding as much, therefore caused the volume to decrease in size. Okay? So then, if you think about the opposite way, if you increase the temperature, increase kinetic energy, more collisions is going to cause the volume of, say, the balloon to expand. All right? So volume goes up as the temperature goes up. Notice that this has the arrows going in the same direction, right? In this case, both of them are going up. So if the relationship is going in the same direction, we call this a direct relationship. So if they're both going up or if they're both going down, then it's considered a direct relationship. Now let's look at the next one. So this next one, as you can see, is a pressure-temperature relationship. So this one is pretty easy. It's very similar to what we had just talked about, increasing temperature, collisions, and all that. So then, let's think about it. The temperature goes up, more kinetic energy, more collisions, therefore the pressure will also go up, correct? So then, what type of relationship is that? Notice that they are both going up. They are both going in the same direction. So this is a direct relationship, right? And we said that this one was direct also. And then the PV relationship was indirect, or you can say inverse. Now, do you see some type of pattern here? Notice the direct relationship ones involve division. The inverse, or the indirect, involves multiplication. So just by looking at the equation here, what type of relationship do you think the volume and moles relationship is going to be? All right, so just by looking at the equation, you should say that that is a direct relationship. Okay, so let's think about it. The number of moles, if that increases, then the volume increases, and that makes sense, right? So that is a direct relationship. So remember, you don't have to have all of the names memorized. You can just think of this combined gas law, right? Let's circle it, that combined gas law. And then if something remains constant, you would just cross it out on both sides. For example, if the temperature is constant or the temperature is not changing, then you would just cross out the T's on both sides. And then you end up with P1V1 equals P2V2. All right? So once again, you don't have to memorize all the separate names and all the separate little equations here. Okay? So you don't need to go and memorize all the separate little equations. Just remember the combined gas law. And then from there, whatever's constant, you just cross out on both sides. Okay, this page right here. All right, so these problems right here, we're actually going to do these in class. Okay, so we're going to do those in class. You don't have to do those right now. All right, the next thing that I want to go over for today has to deal with the ideal gas law. So remember this equation, PV equals nRT. You should probably already have that memorized by now. Take a look at what all the variables represent. Okay, don't forget R is the universal gas constant. This is the R value right there. This R value is in atmospheres. You do need to be careful. There's another R value. It's on your pink sheet. One has joules in it, and this one has atmospheres. So make sure you are using the correct one. Joules represents energy, atmospheres represents pressure. So the values are different. Now, you can use the whole number 0.08206, or sometimes this number here is rounded up to a 1. So if you just put 0.0821, that is okay also. Once again, temperature has to be in Kelvin, all right? When you are using this equation, the units are very, very specific, okay? Pressure has to be in atmospheres. Volume has to be in liters. N, yes, represents moles, okay? That has to be in moles. R is always going to be this number. Temperature always has to be in Kelvin. Once again, the reason why the units are very, very specific is because look at the units in R. Volume is in liters, pressure is in atmospheres, temperature in Kelvin, and then moles. They have to be able to cancel out with these unit values in the R constant. Okay? All right. So then there is this example here that you're going to use, practicing using your PV equals nRT. And then on the next page is another example that you are also going to do in class. All right, you don't have to do those right now. We're going to do those in class. But I want to give you some tips. Now, don't forget that, yes, N represents moles. Okay, but don't forget that you know how to convert grams into moles. So if you're given grams, then you have to convert the grams first into moles, and then you can plug everything else into the equation. All right? So this is the other equation up here that we're going to do in class. You don't have to do it right now. All right? And that is everything. So we're not going to do that quite yet. Just work on this one. Okay? We'll get to that in class the next day. All right, so that is everything for right now, and I will see you later. Bye.